Hi friends, welcome back on our YouTube channel. Here we are with another lecture of classical mechanics in which today we will discuss about generalized momenta and energy. So in the current lecture we will discuss about generalized momentum and also about generalized energy. Now first of all we will discuss about generalized momentum. So let's start with generalized momentum. The canonical momentum for a system having mi mass of ith particle, vi velocity of ith particle. So Newtonian momentum pi is given by mivi. Now the kinetic energy of the system T equal to half mv square, and v is actually velocity and velocity is dx by dt, or this will be x dot. So T equals to half mx dot square. Now if we differentiate T with respect to velocity or with respect to x dot, then half m is constant, so this will be as it is, and the differential of x dot square is twice x dot, and 2 will be cancelled out, so del t by del x dot is mx dot. So this will be mx dot, and mx dot is actually momentum. So in Newtonian mechanics, the Newtonian momentum of ith particle pi is del t upon del xi dot. Since Lagrangian of a system is given by L is equal to T minus V, here T is kinetic energy and V is potential energy. So Lagrangian L equals to T minus V. So here V is actually potential energy. Now if we differentiate this equation with respect to xi dot, then del L upon del xi dot is equal to del T upon del xi dot minus del V upon del xi dot. Since V is independent of velocity and time, V depends only on position because V is actually the potential energy. So V is independent of velocity and time. It means del V upon del xi dot will be 0. So del V upon del xi dot is 0. So this will be 0. It means del L upon del xi dot will be equals to del T upon del xi dot. Since Newtonian momentum pi is equal to del T upon del xi dot, so this is our pi. It means pi is equal to del L upon del xi dot. Therefore, in Lagrangian, pi is equal to del L upon del xi dot. So, the generalized momentum pi is equal to del L upon del qi dot, because here xi is the coordinate of ith particle, and in generalized coordinate we use q in place of x. So xi dot will be qi dot. So generalized momentum is given by pi is equal to del L upon del qi dot. And this is our canonical momentum. So generalized momentum or canonical momentum pi is equal to del L upon del qi dot. Now we take an example. Let m be the mass of a particle and q is its coordinate. Let this particle is moving under a force F equals to minus del V, and V is actually here potential energy. Let the kinetic energy of this particle be T equals to half mx dot square Now Lagrangian L equals to T minus V, and T is half m q dot square. So L equals to half m q dot square minus V. Now we differentiate L with respect to q dot. So del L upon del q dot is equal to half m constant, and differential of q dot square is twice q dot, and V does not depend on velocity, so its differential will be 0. So del L upon del q dot equals to half m into twice q dot, and 2 and 2 will be cancelled out. So this will be m q dot, and q dot is actually velocity, and m into v is actually the momentum. So this will be pi or p. So this 2 and this 2 will be cancelled out. So del L upon del q dot equals to m q dot, and this will be p, which is actually canonical momentum or momentum. So P is equal to del L upon del q dot. Now next one is generalized energy. So what is generalized energy? Let the Lagrangian of a system be L, and L is actually the function of coordinate, velocity and time. That is, L is a function of qi dot and t. Now if we differentiate L with respect to time totally, then dl upon dt is equal to del L upon del t plus del L upon del qi into qi dot plus del L upon del qi dot into qi double dot. Since d by dt of del L upon del qi dot into qi dot, so here we are differentiating this one with respect to time. It means it is the product of two functions. First one is this one and second one is this one. So if del L upon del qi dot is treated as constant and differentiate qi dot with respect to time, so del L upon del qi dot into qi double dot, and second time qi dot is our constant and we differentiate del L upon del qi dot with respect to t, that is d by dt of del L upon del qi dot. Now here we required del L upon del qi dot into qi double dot. It means we are requiring this term, so we transfer this term from here to here. It means del L upon del qi dot qi double dot will be d by dt of del L upon del qi dot into qi dot minus d by dt of del L upon del qi dot. So we get this term. Now we replace this term with this one. So dl by dt is equal to del L by del t, this term as it is, and this one also as it is, and this is replaced with this one. So plus d by dt of del L upon del qi dot minus d by dt of del L upon del qi dot into qi dot. Now this will be dl by dt is equal to del L by del t as it is plus d by dt of del L upon del qi dot into qi dot as it is, and now we take these two terms together and we take qi dot common with negative sign, then this will be minus d by dt of del L upon del qi dot, which is here, minus del L upon del qi, which is here, and qi dot is our common, so dl by dt will be this term. The general form of Euler-Lagrange's equation is d by dt of del L upon del qi dot minus del L upon del qi is equal to capital QI dash. This result we have obtained in our earlier lecture or last lecture, and dl by dt is this one. Since Euler-Lagrange's equation is this one, it means d by dt of del L upon del qi dot minus del L upon del qi can be replaced with capital Qi dash. So dl by dt is equal to del L by del t. This is as it is, and this term is also same, and this one is replaced with Qi dash. So dl by dt is equal to del L by del t plus d by dt of del L upon del Qi dot into Qi dot minus Qi dash into Qi. If the system is non-dissipative, then in non-dissipative system Qi dash into Qi dot equal to 0. So this will be 0. If L is not explicitly time dependent, that is, the system is scleronomic. If L is not explicitly dependent on time, then del L by del t equals to 0. So for non-dissipative system, this term is 0, and for scleronomic system, this term is 0. It means if a system is non-dissipative and scleronomic, then this equation will be dl by dt is equal to d by dt of del L upon del Qi dot. If we transfer this term from here to here, then d by dt is common. So d by dt of del L upon del Qi dot minus L equals to 0. Now we get this term here, and this is known as Jacobian and represented by J. It means dj by dt equals to 0. Since the differential of any quantity is 0, then the quantity will be constant. Since here dj by dt is 0, it means J is constant of motion, and J is actually del L upon del Qi dot minus L, and del L upon del Qi dot is Pi, that is canonical momentum or generalized momentum. It means J is equal to Pi Qi dot minus L. So if we replace this with canonical momentum Pi, then J is equal to Pi Qi dot minus L, and this will be constant of motion. This integral of motion J is called Jacobian or Jacobi integral of the non-dissipative system. So the Jacobi integral of the non-dissipative system is Pi Qi dot minus L, and this is represented with J. Numerically, J represents the total energy of the system or generalized energy of the system, and it is always conserved due to the conservation of energy. Now, we take an example for one particle system. Kinetic energy T equals to half m q dot square. Potential energy is V. Now, Lagrangian L equals to T minus V, and T is this one, and V is our potential energy. So, Lagrangian for one particle system, L is equal to half m q dot square minus V. Since Jacobian, J equals to P q dot minus L, and P is canonical momentum, which is del L upon del Q dot. So if we replace this P with this one, then J equals to del L upon del Q dot into Q dot minus L, and this is our Jacobian. Now Jacobian is this one, and Lagrangian L equals to half m q dot square minus V. So this is our Lagrangian. Now we replace this L and this L with half m q dot square minus V. So J is equal to del by del q dot of half m q dot square minus V, and q dot is this one. minus half m q dot square minus v. Now we differentiate half m q dot square minus v with respect to q dot. So half m is our constant. Differential of q dot square is twice q dot, and v does not depend on velocity or does not depend on q dot, so its differential will be 0. And this q dot as it is, and this term also as it is. Now this 2 and 2 will be cancelled out, so this will be m q dot into q dot, that is q dot square, minus half m q dot square plus v, because this negative and this negative will be positive. Now m q dot square minus half m q dot square will be half m q dot square, and this v is as it is. And this is our kinetic energy, this is potential energy. It means Jacobi is equal to kinetic energy plus potential energy, or Jacobi represents the total energy of the system. So this will be m q dot square minus this term as it is. Now m q dot square minus half m q dot square, half m q dot square, and this v will be as it is. So j equals to half m q dot square plus v, and half m q dot square is kinetic energy of the system, which is represented with T. So L equals to T plus V. It means Lagrangian represents the total mechanical energy of the system. Now here we end our session. So goodbye.